Okay, so thank you for the introduction. So my name is Santiago Velasco Forero. I'm assistant professor in MIN Paris, PSL University. So actually this talk is, I consider like a straightforward talk. It was, I doing in during my holidays actually, last 1 year ago. Like what I was working with some PhD student in equivalent and invariant neural networks from the theoretical point of view, and we have one paper about that. But in many applications, in practical, the use of invariant neural network invariant equivalent neural network was really hard in practice to optimize. So somehow I was asking what happened is we can not use directly this equivalent neural network, but try to induce the invariant, the invariance of the equivalence. So, and after the paper publication, I saw that recently we have papers that are doing similar things. So that's what I didn't include in the paper. So, but what is the context of this paper? So I will work on data-driven models. So we all know now that there are state of the art of many applications in computer vision, especially classification. For example, the case we explained we went to study today. So what is weird is that we use models that have a million of parameters to solve problems, and we can see, for example, in ImageNet that we are able to solve a classification problem on images with more of 1,000 classes, that even better than human beings. So, and the main improvement is that we use more parameters, and in the case of CNS, we include one symmetry, that is the translation equivalent models. So my research is more related in how to try to understand the inductive biases in these models, and using geometric deep learning. So to understand what I did is pretty simple, but we need to have like a common grammar. As basically we have to understand how we train a neural network. So I take some minutes about that. So we have some data. For example, in this case, we have this dog. We have a model that is a compositional model, that is neural network. So we start with a random seed of parameters in neural network. We compute the prediction, and basically what you need to have access is, in the case of supervised learning of CNN or neural network, we have a label. So you have to compare this label and the prediction with a loss function, and we have many possibility of this loss function. In the case of this presentation, I use the categorical cross entropy only, and we minimize this set of parameters in the neural network by backpropagation of the gradient and doing, for example, gradient descent or stochastic gradient descent. So it's pretty simple. So what we know in theory is we have some universal approximation theorem that we know that we can fit pretty easy many function, but the main problem was the problem is that we overfit on training data. So we have data, we really overfit the point. We are not able to generalize in the most simplest case. So one practical solution, and it was my main contribution of Jean Lecan, it was to include the convolutional parts. It means that we impose this translation equivalent property on the network to reduce, like we have the space of multiple function, we reduce the space of function that we are looking of, and we reduce somehow the overfitting of training data. So, but still in this case, in the past we were not able to go really in deep. So the main improvement to be able to apply this model in millions of data, and and many classes was the fact that we can train the data. We can take advantage of the weakness of the training, that is that we take many random images each time to apply a transformation of the data during training. So that is called data augmentation. So it's instead of training only on the original image, we apply random transformation. So that is like a practice cooking receipts to say, okay, you apply some random transformation, even crop and size, or even color distortion, or hiding some part of the edge, rotation, Gaussian noise, whatever, and you train with that data, and you cross fingers and you hope to have a good model. But in the case of overfitting, you can see that okay, as the model is never seeing the object, the main data twice, so it's harder to overfit. So, but however, I work in my research in many applications where we need to include more symmetries. For example, in astronomy. Astronomy, for example, in this case, is important to classify what Hubble stage is each galaxy. So in that case, we know that our solution should be okay. We have one part. The data is not the label data is not available as easy as in computer vision. So we only have access to some images, some patches, for example, the image. So that gives me the idea of use CNN, or the translation equivalent networks. But at the same time, we should add some rotation equivalent symmetry, rotation symmetry. So in this case, okay, that is really easy. But I work also in some more complicated cases, like for example, LiDAR data that have 3D cloud points with the symmetry. You want to include more complicated symmetries and 3D texture shapes. Texture shapes on 3D tomographies, where you can you like to include some symmetries of different types, for example, reflection of something that is very important is the scaling. So in the literature of equivalent neural network, we know that in the simplest case of one is you are able to define a group, like the symmetry as a group. You can use many approaches. If I put some of them, for example, you can use lifting, a convolutional, a deep group space to produce equivalent neural network of group convolutions, and more complicated, more evaluated version, stable filter, tensor field, group PDS. And something that I work on, it was an alternative, but it's just to do some moment publicity about the work, is to formulate something that we call a moving frame net. That is if you are able for a given Lie group, in this case, you can define the fundamental invariant starting from a jet space of Gaussian derivatives, with the condition that you have the guarantee that the convolution, that the filter that you are computing are invariant in the orbit of the group. So we have many alternatives. But the motivation of my working here is to say that in many cases, it's hard in practice to have the group property. For example, even in the scale, you can say to have a group property, I have to be able to go from one object to one element to another element and to go back. So the problem is when you are scaling the object in a discrete sense, when you are going down in scale, you can lose the object completely, or you only have 1 pixel, 2 pixels, and it's impossible to go back. So, and that's why I say that the motivation of this work is to work in no-group transformation. For example, occlusion. It's always hard to go back to the original image or part-based transformation, for example, some not elastic or something more logical transformation. So the approach that I follow is to say, instead of constrained by symmetry, what I only want to use is to use the statistical generalized divergence to push my network to go to the class of symmetry. So how we can do that? So, like I say, I still in the case of the cross-finger algorithms, because we have a guarantee to have the complete symmetry, but the optimization is pretty good. So the main advantage is we can, basically use classical models and only play with the idea of generalized divergence. So what is the idea here is, instead of using only random data augmentation, one will have a set of transformation, and for each one of the transformation I compute the prediction. For example, I illustrate the prediction of k of them as of these probabilities, and I have to compute a measure of invariantness. That meaning I want to reduce the difference between them. So what I'm using here is, in the case of the supervised classification, to use the classical term of supervised classification from the original image, and then use the augmentation as a measure of invariantness. So how to compute the difference between this probability distribution is why I use generalized divergence. For people that don't know what is that, it's basically is a multivariate generalization of statistical divergence. So we have the same properties. We have a set of k distribution of it, and we know that the generalized divergence is positive. It vanishes to zero if we have the equality of the distribution, and it's important if we have invariant permutation of the input component. So in the literature, I took the most oldest article. So we have something in the 1981, the average divergence, basically computing the KL divergence between all the pairs of the probability points, and computed the average, and something that is called information radius, that is even older. So that is basically computing the average of the distributions and computing the k plus 1 average divergence between this center and each one of the divergence. So when I see that actually I include this generalized divergence as a penalization term in the optimization of model of deep learning, I realized that there are many papers that try to do the same. It's the same expression, but the transformation that you use in each one of the instead of use non-group transformation, they use another approach. For example, in semi-supervised learning, the one really paper that use change perturbation of the data. Once it's self-training, for example, you can use pseudo labels instead of perturbations in for the documentation, and we have something that is really hot topic now, that's self-supervised learning, that you can rewrite some of the expressions that they use in the same way. And recently there are many papers using what they call data augmentation regularization, that is the same framework that here, but not in the case of no group invariance, no group transformations. So the experiment that I want to use is something that I try to analyze a problem that is really hard, because I have two data sets. We have in the first, we have traffic sign data set. We have images. We have existing classes, and actually we have a data set from this paper that provides for each one of the images the version that change the scale and is translated also. So that's important to say that, for example, if you want to modelize this image of group transformation, when you're going from here to here, sometimes you can include, have a border effect. You know, actually have to know where is the object to compute the invert. So that is, I mean, it's impossible to, you have to solve the identification problem to compute the invert. So it's impossible to modelize in rare images with the group transformation, this scale changes. And then here you can see that, for example, in this image, even when you zoom in, you lost one of the objects. So that is, I mean, for me, it's really, I mean, it's a hard problem. So to become even harder, we follow one of the protocol proposed in this paper. So we train only with the middle scales and want to test the performance of the model in different, I mean, out of the scale images. And this way we can really see if the effect of computing or adding this regularization of the with the generalized divergence. So I try to follow the same protocol that they use here. So you have only 2 layers of model, so it's really not as big as possible, but it's only a matter of for purpose of fairness. So, and I fix the number of transformations that I'm using as k equal to 3, only to illustrate the approach. So I have a table, but it's better to see in this way. So in blue line is the training, the testing accuracy of the model when using classical approach, the data augmentation, where you have the performance in blue is in the training scale. So as soon as you are going reducing the scale, so increasing the scale of the image, your performance reduce. And using, for example, information radius regularization with alpha lambda equal to 2, you have improvement in out of the scale. But even that's something that is really, what was a strength for me is that even in the training scale, you have better performance. So that idea of forcing or inducing this symmetry improve the performance even in the scale that they are the training. So I have the same in traffic sign dataset. So when we come back to the table, we basically, we don't have actually quantitative difference between average divergence or information radius, and we can, I mean, have an hypothesis that actually you can, lambda, you can deal as hyperparameter, you can optimize that. And you always have an improvement with respect to that augmentation. So, and okay, for only the conclusion, you have the price to pay is actually during training you have to compute a multiple prediction, but in testing actually it's as fast as a classical model. And only to illustrate that is a graphical expression that what we are trying to optimize, because actually the categorical cross entropy is equal to the divergence plus the entropy of the ground truth. So you see all of them as entropies. Basically, the augmentation is choosing one of the augmentation to compute this divergence between the augmented data and the true labels. And what we are doing now in our proposition is to compute the divergence to the prediction in the real data and regularizing we can say the volume of this many transformation. So that is why I say I mean this, like what I'm doing now is try to prove that actually this model, I mean the stochastic gradient descent applying this kind of optimization problem converge. That's because it's not in practice we can see it, but not so clear for me. And okay, that's it. Okay, thank you.
Okay, so in view of time, there's room for a few short questions. Okay.
You showed that occlusion is not a group transformation, but you could think about permutation of pixels and recover discrete symmetries and work with this. It comes almost to the same.
Yeah, but the occlusion includes new pixel information that you are not in the original image. Yeah, but there are some particular case of occlusion that can be modelized as group transformation, I agree, but not in general, because you can add pixels that are not in the original image. Okay.
But maybe permutation are much better than occlusion.
Yeah, but permutation is, I mean, you can, yeah, I mean, it's the most strongest assumption, but I mean, there are cases of occlusion that even in permutation cannot cover. Yeah. There's another question there as well.
There was still a question here?
No?
No. Okay, then yeah, maybe also in the interest of time, let's move on to the last speaker. Let's thank Santiago.